I want to show you the derivation more along the lines of what's suggested in the book of problem 49. This is showing that if I have a function, two functions f and g of just one variable, and that's important, that f and g themselves are just functions of one variable, but then I take f of x plus at, where a is a constant, and g of x minus at, and I add them together, that this function has a very special property, and the claim is that it satisfies the wave equation. And we talked about that. I did a video about that a little bit last semester. And it's about the second derivatives of this function. And the suggestion that I had in class was to split it up into just the f part and the g part, prove that for this separately, and then combine them. And that has the advantage of simplifying things into a simpler tree, where you have just f of this one quantity x plus at, and then that depends on x and t separately. But let me show you how it would work combining them, because it's a good thing to do, and it has a similar brings up similar issues. So, what's the tree diagram here? Well, let's name these intermediate quantities as they suggest. U is x plus at, v equals x minus at. And so the tree is that z depends on u and v, and u and v both depend on x and t. And we often want to name the functions as well. Well, here u is x plus at. I don't think I have a real need to name that, because its derivatives are going to be really simple. Similarly for v. And then z depends on u and v. Well, I don't have a name yet for that. Let's say this is h of u and v, the sum of those two guys. And we used h for a similar purpose in class. That might be helpful to have that notation there. Okay, so let's go ahead and calculate one of the sides of this. Let's go ahead and calculate. We'll start with the first derivative, dz dt, and use the chain rule. So that's going to be how z depends on u times du dt plus how does z depend on v times dv dt. Now, dz du, that's, in other words, it's the partial derivative of h with respect to u. Well, h of uv, that's f of u plus g of v, and that's in a very special form. The f function only depends on u, and g only depends on v. So the partial derivative of z with respect to u, well, with respect to u, this is constant. G of v is constant. F of u is the only thing that is going to have a derivative there, and that's just going to be f prime of u. Now du dt, that's on the downstairs branch here, and that has to do with this very explicit formula. Du dt is just a. Now dz dv, that's going to be the derivative of this function h, or in other words f plus g, with respect to v. Now this guy's a constant, and we just get g prime of v. What I'm doing with the primes here is, when a function is just a function of one variable, you can use ordinary one-variable notation, but you have to be really sure that it is really just a function of one variable to make the primes make any sense. Never, ever use a prime to indicate a partial derivative, because that's just going to be horribly confusing to you and everybody who reads it. Now, dv dt is minus a. Okay. So, that's dz by dt. Now, I want to take the second derivative of that. And the key thing here is that that's the first derivative of a first derivative. And so I'm going to be taking the first derivative with respect to t of this whole thing, and f prime of u is a function. It happens to be a function of just a function of u. This is a function of v. They're both things where the multivariable chain rule totally applies. This whole combination, in fact, has exactly the same shape in terms of the tree as this guy does. It has exactly this tree. The output of this is some quantity. We wouldn't want to call it z because it's not really the same thing. But it's a quantity that it depends on u and v. And u and v, of course, depend on x and t. And so we could actually do the whole thing all at once and put it into this tree diagram. It's going to be simpler, and this is a little bit like what the strategy you guys suggested in class, to go ahead and separate it out. And the a's come out, definitely. And then minus d by dt, g prime of v. And the thing about taking second derivatives is always to just realize, don't be scared about the fact that this has a derivative in it already. Just suppose somebody gave you this function f prime and just said, oh, yeah, it's this weird notation, I just happen to put a prime here. It's just some function. You can still use the chain rule, and you just plug in f prime everywhere where the chain rule would say. So that's going to be a, and so d by dt, f prime of u, I bet, can you see that? Yeah. D by dt f prime of u is going to be expanded out in the usual way. And so that's going to be, well, let's actually, we could do it two ways. We could ignore the fact that this only depends on u, and we could do it as this whole tree with u, v, x, and t. But you know what? The tree for f prime, I don't know, I don't want to name that. The tree for f prime, it really only depends on u. So it's going to be the simpler case of the multivariable chain rule, where the derivative with respect to t is just the derivative of this one times the derivative of this guy. So that's going to be the derivative with respect to u, now that's ordinary, because there's only one, of f prime of u, times, oh, now that's a partial, very sorry, du, partial u, partial t. And then the other one, coming from d by dt of g prime, oh, the a is a overall factor. Oh, and that's minus, very sorry. Minus d by dv, because that's for g prime, it only depends on v. d by dv of g prime of v times partial v, partial t. Okay. Well, if this was already a first derivative, and you're taking another ordinary derivative, so that's just f double prime. Du dt, partial u, partial t, is a. And then here, this is g double prime of v, and partial v, partial t is minus a. Oh, that's a common factor, sorry. So we get a squared, and then a plus a squared, so it's all a squared plus g double prime of v. So that's half of the calculation. That's d squared z partial squared z partial t squared. Now, if you look at how that worked, that was taking derivatives with respect to t. The derivatives with respect to x are going to be extremely similar. I'm not going to write them out. Every time you get instead of a t, you're going to get an x. And the only thing that's going to be different is this a here. Right here. It's really right here. The du dt was an a. Now du dx is going to be 1, and dv dx is going to be 1. So all these terms are just going to be 1s instead of plus or minus a's. And so we're going to get d squared z dx squared is exactly just f double prime of u plus g double prime of v. And so, comparing them, we see that this is a squared times that. And I'll stop there, and we'll do another video in a sec.